about 300 words of text on the back, so as much information as we can pack into that many words, as well as some references for places to learn more. Our speaker tonight is Dr. Brandon Lawton, also of the Office of Public Outreach, and he'll be talking to you about Hubble's views of the deep universe, which is obviously a popular topic because we have such a crowd here tonight. No pressure on you, Brandon, okay? No pressure, okay? Upcoming, we have a complete schedule. This is the first time in a few months I've had a complete schedule because I've been busy doing other things, and this month I really put my nose to the grindstone and made sure I had speakers for the upcoming months. Next month, I've had Lucy McFadden scheduled for a while. She will be talking to you about the other major solar system mission, the Dawn mission, that has visited the asteroids Vesta and Ceres and is still in orbit around Ceres. So this is really cool. She's coming up to us from the Goddard Space Flight Center. On January, we have a trifecta of Vanessa Thomas, Max Muchler, and Rosa Diaz. They went to the White House for White House Astronomy Night 2015, and they have agreed to come in and share their experiences. How many of you, this is an interesting question for how many old-timers we've got. How many of you were here in 2009 when Vanessa and Max talked about the White House Star Party in 2009? Raise your hands. Okay, so we've got a handful of old-timers who are here, okay? The rest of you, hopefully in 5 years when I ask the next question, you all will raise your hands as well. We got a lot of people who've been here consistently for years and years and years. And then in February, a talk I'm really looking forward to is called The Southern Skies, Astronomy in Chile. If you do not know, there are about a dozen major astronomical observatories in Chile. And matter of fact, when I was researching it for an educational talk I was doing, I found that they have actually a website on astronomical tourism in Chile. Okay? So Mia Bovel is going to come and tell us about that on Groundhog Day 2016. If you want to be reminded of this, you can go to our website. If you just search for Hubble Public Talks on your favorite search engine, you should come up with this web page, which has a list of our upcoming lectures over here, as well as a link to the STSCI webcasting site for our archive of lectures all the way back to 2005. For 10 years, we have been webcasting, so you get 10 years of astronomy lectures to watch, okay? It's going to take you more than just a day or two to go through them all. Let's see, what else? If you would also like an email in your inbox to tell you about what's coming up, you can sign up at this website, maillist.stsci.edu. Notice that there's a double L in there. You click on the one that says Public Lecture Announce and add your email address to it. And you won't get any spam, okay? We've got a very secure mailing list system, so that works fine. Or you can just provide your email address to me, easy enough to do by sending it to publiclecture@stsci.edu. That is the email address we've established for comments and questions, and if you want to sign up for the announcement list, you can send it there as well. If you would like to follow the Hubble Space Telescope on social media, we are on Facebook. We've got 2 Twitter accounts. We're on Google+. We're on Pinterest. Are there other ones we're on? Probably. I only keep up with so much. Myself, I have a blog on Hubble site. I'm on Facebook. I'm on Google+, and I'm on Twitter, but I only do them sparingly, so don't expect to see 10 or 12 messages a day from me, okay? 1 message a day is good for me when I get things out on social media, okay? After the talk tonight, the weather is permitting, so you will have the observatory. The observatory will be open. I got the email. So the Maryland Space Grant Observatory staff will be here. We'll, at the end of the lecture, make sure you remind me that I say, okay, anybody who wants to go to the observatory, come over here and go across the street. And what's interesting tonight is that there may be a chance of seeing the aurora, okay? It's been all over some of the internet things tonight that the aurora are extra large right now. There was one web page that said it may be viewable as far south as South Carolina. This is not what AccuWeather says. This comes from AccuWeather.com, and you can see Maryland right there is in the green. That says good visibility. Now, somebody said that they looked for it already this evening, couldn't see anything yet, but aurora are highly variable. We don't know if you're going to be able to see them, but if you go across the street to the observatory, I'm sure the folks over there will help you look for it. All right? Okay, so let's do our news from the universe for November 2015. Our top story tonight, examining infant solar systems. Now, we have been looking at solar systems in formation for about 20 years. The sort of seminal press release on this was in 1995 when Hubble released this image of the Orion Nebula. Now, the Orion Nebula is a star-forming region, and the stars in it are about 2 million years old. But in addition to seeing the newborn stars, we also can see newborn stars with disks around them. So here on the left, you see the newborn star in the center, and you see that dark dust disk around it. Okay, here you can see the star isn't quite so bright, and here you see a beautiful dust disk, okay? And as a star forms, material forms into a disk around it, and inside those disks are where planets will form. So this was sort of the first, seminal release that said to me, wow, we really can start studying solar systems in formation. And we have followed on seeing a lot of disks around young stars. So here are two, AU microscopy and HD 107146, that I love to use these two. In both of these, the light of the star has been blocked so that you can see the disks around them. And AU microscopy gives you a beautiful edge-on disk, and HD 107146 gives you a beautiful face-on disk. So we can really start to see the disks around other stars. But what we really want to see is we want to see the planets. We want to see evidence that there are planets forming in these disks. And the most famous one where we had evidence that a planet should be there is the star Fomalhaut. Okay? Now again, the light of Fomalhaut has been blocked so that you can see this ring around Fomalhaut. Okay? And this ring was off-center, indicating there might be a planet that's tugging it off-center. Okay? So the presence of planets has a gravitational effect on disks and rings that can be show up to show their presence. And it turned out that this little red dot right there is what we believe to be planet Fomalhaut b, and that it was moving on the correct orbit in order to pull that ring off center. We got even more spectacular evidence of planets forming in a disk from the Atacama Large Millimeter Array, which, by the way, is in Chile. The ALMA array took this millimeter wave image of the star HL Tauri, and here you can see amazing gaps. This is not an artist's drawing. This is a real image, and you can see the gaps pulled out in the system due to most likely due to the presence of planets. So we've been looking for several ways, trying to find evidence of planets. And we actually have one more really good piece of evidence of planets. And in some systems, we have seen spiral waves. This is the first time I became aware of it for our press release last month. And that in some of these stars, this one is called MCW 758. Not a very poetic name, but we can see that there are these sort of spiral long tails. All right? And these were relatively unexplained. We thought they might be due to planets, but we weren't able to prove it until a team studying these stars did a computer simulation, a whole bunch of computer simulations, trying to reproduce this effect by putting a planet in there. So here, this is a real image. This is a simulated image of a disk with a planet. And the planet in this disk is not represented in the density, but it's actually would be located right about there. So having the planet in the disk can create the resonances that allow these spiral waves to occur. So this isn't proof that there's a planet in this system, but it's a very strong evidence that, yes, planets can produce these spiral waves. And so when we see these spiral waves, we should go searching to see if we can find planets in them. All right? So we're getting a larger and larger number of ways of examining these infinite solar systems and trying to find evidence of planets in there. We have observed lots of planets either indirectly due to the wobble they produce in their star or the changes in the light, but we can also, and I think these are more interesting and more visually satisfying, find evidence of planets by looking at those disks. Okay? Our second story is not the winds of change. So Hubble has looked at the planet Jupiter many, many, many times over its 25-year history. One of its most famous ones is 1994, the comet Shoemaker-Levy 9 impacts. And here the visible light where you can see the impacts, and here is ultraviolet light where you can see the impacts even a little bit better. And we looked in 2008 when we got to see 3 red spots on Jupiter, the Great Red Spot, the Red Spot Junior, and the Baby Red Spot, which unfortunately was destroyed during the summer of 2008 as it got caught in the vortices of the Great Red Spot. And we have followed the Great Red Spot for years, and we did a press release last year about how the Great Red Spot is actually shrinking. So we have followed the Jupiter for many, many years. So we keep taking images and over and over again, and we finally have codified this into a yearly program. And so this yearly program is called OPAL, the Outer Planet Archive Legacy Program. That's one of the better acronyms. We astronomers are pretty bad at creating acronyms, but OPAL, I actually kind of like that one, okay? And so the idea is that we will take high-resolution pictures of all the outer planets, Jupiter, Saturn, Uranus, and Neptune, every year to track the changes in them and to understand the changes in them over the years. And so we'll have one of the legacies of Hubble will be that we'll have in the archive yearly pictures of the giant planets so that we can track the changes that are going on in them. And matter of fact, in this press release, we took 2 images of it, basically 2 successive rotations of Jupiter. And so this is the first one, and you gotta watch really carefully to see the changes. And here's the second one. There's the first one, and there's the second one. The first one, and the second one. Not very big changes, but, you know, getting 2 rotations of Jupiter, being able to understand the motions of the clouds in Jupiter, okay? And when this was released, there was actually a little bit of, fanfare on the internet that we had 4K images of Jupiter. All right, I don't know if you guys know, but the next thing in television is called UHD, which is 4 times the resolution of full HD. It's 3840 by like 2160 pixels. And so if you go to your local store, you can buy a UHD television. There's almost no programming for it that actually is in UHD except for the demo programs they play in the store. But, you know, eventually there will be some UHD. And that's also called 4K in movie parlance. And so there was big stuff. Hubble has images of Jupiter in 4K. Well, I hate to burst their bubble, but Hubble is not the first to get Jupiter in 4K. In 2006, 9 years ago, the Cassini mission released this map of Jupiter at even higher resolution than Hubble produced, okay? So I gotta think that the Cassini folks are going, why are they getting all this press of 4K on Jupiter when, you know, they had done this almost a decade earlier? Well, 4K television wasn't out at the time, so it wasn't something to note. All right, so the internet wasn't gonna fall for it. All right, so that isn't actually, the 4K isn't the real story here. The point is that they're trying to look for these special features on Jupiter and track the changes on Jupiter. And so our press release talked about some interesting features in the Great Red Spot. All right, and there's a feature here, okay, that stretches across the Great Red Spot, and this is the orbit 1 and orbit 2, okay? And you can see this feature here. This is a very unusual feature in the Great Red Spot. They also examined the images, and they found what's called a baroclinic wave, okay? A baroclinic wave that had not been seen on Jupiter since the Voyager missions to Jupiter 20 years ago. So these long-term observations of Jupiter do provide, patterns of what's going on Jupiter and catch the rare events. But actually, for me, the coolest result was just a graph in their paper, okay? And this is the graph in the paper. I know it's geeky and everything, but let me explain it to you and show you why it's actually kind of cool. All right, so on the y-axis here, we have the latitude. So that's north and south on Jupiter. And on the x-axis, we have the wind speed. And what you can see is that the winds go east, and then they go west, and they go east and west, and east and west, and they go back and forth. And if I overlay this on top of an image of Jupiter, you can see that the zones actually correspond to the changes in the clouds on Jupiter, okay? So that you can see that, all right, so this is going this way and this part is going that way, all right? And you can see how the winds change. But the most important thing is that the winds don't change over time, because the red line is the Voyager mission from 1979. The blue line is Cassini measurements in 2000, and the black line is HST in 2015. So we're talking 35 years, 36 years of measurements of the zonal winds on Jupiter, and they have the same pattern. They haven't changed in 36 years. And that's why I called this story Not the Winds of Change, because although there's lots of winds going opposite directions, they are relatively stable. And I found that result really remarkable. Okay, so that is our news for tonight. And now let me introduce our featured speaker. Our speaker tonight is my very dear friend, Dr. Brandon Lawton. He is also in the Office of Public Outreach here at the Space Telescope Science Institute. He joined us in 2008 as a postdoc, working not on Hubble data, but on Spitzer data. All right, and he did has done a lot of his research on dust in the galaxy. And sometimes we kid him about dust and everything. We have the jokes about, we have a specialist in solar system stuff, and I'm more of a specialist in cosmology stuff. And he sweeps up all the dust in the universe and takes care of that. He is a fantastic guy and a wonderful speaker. Ladies and gentlemen, Dr. Brandon Lawton.
Thank you. Thank you very much, Frank. All right. This is a nice audience. Wow. This is really, fill a room. Okay, I'm really pleased to be here tonight. Make sure it stays on. There we go. Okay, I'll just hold on to it. It seems to go off every time I put it in my pocket. All right. Okay, so as many of you may be aware, this is 25 years the Hubble has been, operating in space, right? So it was launched in April of 1990, okay? And I challenge any of you after, not now, because I want you to pay attention to me, but after this, to go onto Google and just do a Google search for the most important image ever taken. Just that simple thing. And I think that you'll find some of the images I show you today pop up near the top, if not at the top of that list. Okay, so what I'm going to talk to you today is about Hubble's views of the deep universe, really the deep fields and what we're doing now since the deep fields and pushing forward in the deep universe. Okay, but I like to start this story by getting sort of the basics, because a lot of what I'm going to talk about are about galaxies. Okay, so here is an artist's impression of our own Milky Way galaxy. All right. Now we like to say, okay, what is in a galaxy, right? So this is our galaxy, and of course we have planets and moons. So here's where our solar system is located in the Milky Way. Okay, so we have planets and moons like the Earth and Mars, Saturn, and so on. Okay, we also have lots of stars in our galaxy. All right, so this is an image here of Omega Centauri, a big star cluster. And what you'll notice about the stars in this picture and stars in general is they come in a variety of colors. Okay. And so a lot of the colors we see from galaxies come from simply the colors of the stars in those galaxies. Okay? All right. We have gas and dust, one of my favorite things to study, as Frank was mentioning. Gas and dust are really the places in a galaxy where you can form new stars. Okay, so there are places where new stars form from the gas and dust. Stars, when they die, can also give back a lot of gas and dust to the interstellar medium, from which new stars can then form from this, what we call enriched, more metallic gas and dust. Okay. You'll also notice that gas and dust, you can see in visible light that the gas and dust largely blocks out the light from behind it, so it doesn't shine in visible light like we use Hubble for a lot of visible observations, but it blocks out the visible light. And visible light, you really see a lot of the stars here. Okay. All right. So let's take a step back. All right. So we're going to talk about studying about galaxies. Well, let's take a step back and let's just do a thought experiment. All right. So here's planet Earth, obviously, right? So let's just do a thought experiment where, say, you're an astronaut floating above the Earth, okay? And you wanted to understand everything you could about humans on Earth, okay? But you didn't have direct contact with people on Earth, all right? So you wanted to know how are humans born? What is the variety of humanity on Earth, right? Do humans come in different sizes, for example? I think I'm evidence that yes. So I'm just going to put this out there as a thought experiment. What might you do to study humanity if you couldn't contact humans directly? What might you do? You can just shout it out if you have an idea. Take a picture. Wonderful. You could take a picture. All right? Let's say you take a picture. You have this picture of this girl on the beach. All right? Does this encompass humanity? No. It's a great picture, but right, we have to do better. All right? All right, now we're getting some more variety. We're starting to understand that there's variety in humans. Okay, let's keep going. All right, let's keep going. Okay, you're starting to get the idea, right, that if you take enough pictures of enough people, you'll start to be able to piece together that there are young people, there are older people, there are people that come in different sizes, and so on. You'll start to get the true variety of humans on the Earth if you take enough pictures, right? And this is actually a lot easier, for example, than following an individual throughout their whole life to see how humans vary with time. If you just take enough pictures, you can sample or get a statistical sample of what humans are like throughout their entire lifespan. Okay? Well, that's exactly what astronomers have to do when they study galaxies, right? We can't go to the galaxies. We can't ask them, hey, how were you born, right? All we can do is we can take pictures, right? We get the light from those galaxies, okay? And if we get enough images of galaxies, okay, we can start to piece together how are galaxies born, how do galaxies change with time, and so on. We get the full, if you will, galaxy zoo, or variety of galaxies in the universe, if we take enough pictures. So we've done this in the local universe. Okay? So nearby, we've done this, and we notice that galaxies come in three sort of bins of morphology or shape. Okay? So on the left here, you have spirals like our own Milky Way galaxy. Okay, spirals are sort of disc shaped. So if you imagine a frisbee, this is what it would look like face on, right? The frisbee face on, you see the spiral arm structure, and if you look at it edge on, it's more like a disc, right? And you'll notice, like I mentioned before, you see various colors in the galaxy. Now, we notice there's a lot of blue light in the spiral arms. Those come from the blue stars, which if you see blue stars in a galaxy, it tells you that there's star formation going on in the galaxy, okay? Because young star-forming regions tend to give off a lot of blue light. So if you see blue, it tells you there's young stars or current star formation going on in the galaxy. So there's current star formation going on typically in spiral galaxies. In the centers, you'll notice it's actually more red or yellow. So there's older stars there. Okay, that's very typical for spiral galaxies. Ellipticals, these are like spheroidal shape or football shaped, if you will. Okay, these galaxies tend to be redder in color. They tend to be made up mostly of older stars. There's not as much gas and dust in these elliptical galaxies as there are in spiral galaxies. And then we put the sort of everything else bin, right? The irregular. If it doesn't follow the sort of the elliptical or spiral shape, we put it in the irregular bin. And there's a lot of variable, these vary in color and shape, of course, but we do find that a lot of them are undergoing sort of gravitational interactions with other galaxies, which causes that sort of strange shape that you see. And a lot of them do tend to be blue and have current star formation going on. Okay, so that's what we've learned in the nearby universe. Now, but let's talk about the deep universe, because that's what we're here to talk about, right? The deep universe. So let me start by saying this really got started in, the observations were done in 1995, and this image here of the Hubble Deep Field, which is the first deep field, was released in early 1996. Now, when I show these sort of pictures of the various deep fields, I'm going to put the PI of the program here. This is Bob Williams, Dr. Bob Williams, who works here at the Space Telescope Science Institute. In fact, he's probably given a public lecture series before, okay? So you can probably find that if you've seen him talk. He's a wonderful speaker. And Bob Williams at the time, in 1995, he was the director of the Space Telescope Science Institute. And what people may not realize is that the director of the Space Telescope Science Institute has what's called director's discretionary time, which is time to use on Hubble that they want to use for, you know, whatever purpose they see fit. Usually, historically, before this, and mostly since then as well, what they tend to do is they tend to choose science observations that the astronomical community is really striving for, that didn't make it through the proposal process and so on. Okay. However, in this instance, Dr. Williams decided that he would do maybe one of the most basic science experiments you could imagine, which is, let's take a look at a really basically a blank patch of sky. Okay? And let's point Hubble there and stare at it for about 10 days and just see what we get. Okay? And this is what we got, and this blew everyone away. There's about 3,000 galaxies in this image. Almost everything here is a galaxy. Okay? Even these little, I'll even use my fingers, even these little smudges that you can barely see are individual galaxies in the deep universe. The only things that aren't galaxies in here are these little cross-shaped things. These are stars. There's a few of them in the image. These are stars in our own galaxy that we're looking past. Okay? And there's a few. But most everything in this is a galaxy, okay? So again, 10 days observing to get this image, and it really blew everyone's mind out of the water. So to give you an idea about the patch of sky that Hubble looked at to get this, if you hold a dime up at arm's length, all right, it's equivalent to, Hubble can see the equivalent to about the eyeball of FDR on the dime held at arm's length. That's the size that we're talking about when Hubble took this image. Very small patch of sky. We saw about 3,000 galaxies. Okay. Now, this started the science process. In 1998, it was followed up by more director's discretionary time to redo the experiment in the southern hemisphere. Because again, if you have one sight line in the deep universe, you might see some results and you might think, is that representative of the whole universe? Or maybe we saw some special patch of sky. Let's redo the experiment. And there were other reasons why they wanted to do it in the southern hemisphere. But let's redo the experiment and see if we get about the same results. And they did. They got about the same results. And this is called the Hubble Deep Field South. And if there's questions, I can talk about other science that came from this that was unique to this that wasn't included in the Hubble Deep Field North. But for time's sake, we can move on. But basically, they got about the same results as the Hubble Deep Field North in terms of numbers of galaxies that were observed. Okay. All right. And now we're going to move forward to 2004. Okay, and so here's Dr. Stephen Beckwith. He was the director of Space Telescope Science Institute at the time, and he had director's discretionary time. And basically, they wanted to redo the experiment with Hubble to do another deep field, right? They call this one the Hubble Ultra Deep Field because ultra is better, right? That's what it means, right? So they called it the Hubble Ultra Deep Field. It was deeper. Now, the reason I told you that it was about 10 days of observing time for the original Hubble Deep Field. This one is about 11 days. So it really wasn't the observing time that made this image deeper to image the fainter galaxies that they didn't see before in this patch of sky, right? Again, this is a whole different patch of sky in the southern hemisphere that they did not image before. It was really that in 2002, there was a Hubble servicing mission, and the astronauts put up more sensitive instruments and more sensitive cameras. And it's really the sensitive camera on Hubble at the time, the Advanced Camera for Surveys, the ACS instrument, that really produced this amazing, astounding result. This image here, for about the same exposure time as the original Hubble Deep Field, instead of about 3,000 galaxies in this image, there are about 10,000. Okay, so we're seeing even deeper. Okay, we're seeing even deeper into the universe. Okay, all right. I wanted to show you just sort of the patch of sky. I'll explain what XDF means in a minute, but just know this is about the patch of sky that we're talking about relative to the full moon, and this even exaggerates the size of the full moon, because if you actually go out in the night sky, the full moon doesn't take this much of the, right? It's the screen blowing it up a bit, but it would take about 14 or 15 of these Hubble Deep Fields or Hubble Ultra Deep Fields to span the width of the full moon, okay? So it's a small patch of sky, and the full moon is about 1/2 degree on the sky. All right, so So again, it's a very small patch of sky. And if you do the experiment with the Hubble Ultra Deep Field, where you take that small patch of sky, right, and we know we had about 10,000 galaxies, you do the simple mathematical experiment where you decide, okay, how many of those would it take to cover the whole sky if we wanted to observe the whole universe, right? It would take almost 13 million Hubble Ultra Deep Fields to cover the whole sky. Okay? So if you do the simple calculation, one Hubble Ultra Deep Field has about 10,000 galaxies, and you multiply that by about 13 million, little 12,700,000 if you want to be exact, okay? But if you do that calculation, right, you're going to get that there are several hundred billion galaxies in the observable universe, right? This should blow your mind. I should hear, whoa, right? This should blow your mind. There's several hundred billion galaxies in the observable universe, right? Each galaxy contains billions of stars, billions of planets, right? This tells you the immensity. One of the reasons why these are the most important images ever taken, right, is because it puts things in perspective for humanity, right? There's only a few images in the history of humans, right, that really puts things in perspective. I would argue that one of them is when the first Apollo mission went around the moon and they saw the blue marble of Earth from the opposite side of the moon, right? That really put things in perspective. We saw how, we saw our Earth and everyone basically on the Earth as in one image before, right? I would put this up there to show the perspective and the immensity of the universe, okay? Here's just some snapshots of the Hubble Ultra Deep Field, just to show you that when you look at this, right, you see a variety of galaxy shapes and colors and so on. So you see things like in the far upper right corner here, you see a typical sort of spiral galaxy, which is nearer to us, but you also see a lot of what you might call train wreck galaxies, galaxies that are very irregular in shape, that have these really strange shapes, all right? And as it turns out, as we know now from the deep fields, the further back, or the further away in the deep universe you look, the more of these sort of train wreck galaxies we find. And I'll explain that. Okay. All right, so let's talk about this. So we've talked about, Hubble really, these deep fields are really looking at galaxies in the distant universe, right? But it's not just looking at galaxies in the, spatially in the distant universe. It's also looking at galaxies at different times, okay? So we like to say that telescopes are time machines, and it's really true, okay? The further away you look in the universe, the further back in time you are looking, okay? This is sort of a schematic to show you. At this far end here, we have the Big Bang. That happened about 13.8 billion years ago, give or take a few days, right? And as the universe is expanding with time, you'll see, the galaxies start to form at some point after the Big Bang, and they start to get bigger and do these more majestic spiral shapes and ellipticals and so on. So time is basically moving forward, and we like to call these Hubble Deep Fields sort of like core samples into the universe, right? Again, they're very small patches of the sky that they're observing, but they're going very deep, okay? And so basically what's going on here, right, is that light from the most distant galaxies took a long time to reach us. Light has a speed limit. It takes a long time to reach us. So by the time that it gets to us, it's been 13-something billion years, okay, for the most distant galaxies, right? So this would be like if you have family so we're in Baltimore, so you have family in California, right? And they send a postcard of themselves or your family, and they send it in the mail. And I don't mean electronic mail. I mean the what we call snail mail now. But they send it through the post office, and it gets lost for 5 years. And then you get it 5 years later, and you look at it, and you're like, oh, that's a picture of my family. I know what that is, but that's not what they look like today, right? We're getting old pictures of the universe, okay? The further away we look, the older the pictures are, because light takes time to travel, right? Okay, so, and that's actually very useful, because with this technique, we can actually study then what galaxies look like in the early universe when they're babies, okay, if we can look back far enough, and we can see how they change with time. And the ultimate goal, right, is to understand how is it that we got to be here in our beautiful spiral Milky Way galaxy. But to understand how our Milky Way galaxy got here and how we got to be in this Milky Way galaxy, we have to understand where galaxies like the Milky Way came from, all right? Okay, all right. There's another little hitch to this that I'm going to talk about. It has a nice technical term called cosmological redshift, which I'm going to play a little demonstration of. This is simply to say that as the universe is, the universe is expanding with time, right? So after the Big Bang, the universe is expanding with time. Space itself is stretching, it's getting bigger. And that does a funny thing to the light. So let's say this light bulb is a distant galaxy and it's emitting blue light. Let's say it's having a lot of new star formation going on, which gives off blue light, like I mentioned before. As that blue light travels through the universe, I'll play this movie here, you'll notice that space is stretching, and it's stretching the wavelength of light as it's trying to traverse the universe. If it's far enough and it takes long enough to get here, it will be red by the time it gets to us. I'll play that one more time. This is called redshift or cosmological redshift. Okay? So by the time it gets to us, that light is red. And so it's not red intrinsically. It's not red because the light left that galaxy red. It's red because it's been redshifted from the expanding universe. And so we have to take that into account when we study these really distant galaxies. Because if they're really distant, their light has been shifted considerably into the red. All right. In fact, here is a sample from a Hubble survey called GOODS. This is from the deep fields, but this is a survey of spirals. And GOODS did not look as deep as the deep fields, but it did a sort of a larger survey of the sky. And you can see from this that spiral galaxies in the very far universe, and looking back further in time, they tend to be smaller, right? Their structure is a little bit more messy, and they were redder. And as you get closer to the nearby universe, they are larger. Their structures are a bit more pristine, right? You have these beautiful spiral shapes for the galaxies. Now, and a lot of this is what you're seeing is actually happening. Galaxies are getting bigger with time. They're getting more organized. Spiral galaxies typically as a class are getting more organized in their shape. But this redness, a lot of the redness you see from these distant galaxies are actually caused by that cosmological redshift. They're not intrinsically red. They're not actually red. They're red because the light that we see from them has been stretched. And so we have to take that into account. Okay. All right. So I want to go, I say all that because, you know, Hubble has capabilities to see invisible light, but until 2009, right? Now I'm showing, again, the original Hubble Ultra Deep Field here, but until 2009, Hubble did not really have much infrared capability. Now, if you know anything about infrared light, it's basically longer wavelengths, redder light than red light that we can see. Okay? So it's invisible type of light that our eyes can't see. But in 2009, there was another servicing mission of Hubble, and they put on an instrument, the Wide Field Camera 3, that had infrared capabilities to see sort of near infrared light, right? Again, why is this important? One of the goals, right, is to catch the galaxies that are so far away that they've been reddened so much that they're now reddened into the infrared, that Hubble could not have seen them before. Okay, because now the wavelengths are stretched so much, you just have to have a capability to see an infrared to see them. And so I just wanted to put up here, here's the original Hubble Ultra Deep Field, and they did a follow-up after that servicing mission in 2009 with that new camera. Now I put the square up here just to show you that the new camera has a slightly smaller field of view than that original Hubble Ultra Deep Field. It's actually looking at this patch in the square. Okay, slightly smaller field of view, but way more sensitive to infrared light. Okay, and that's what you get with the Hubble Ultra Deep Field version 2009. Okay, now this really got us looking back really far in the universe. This, again, Dr. Garth Illingworth was the PI here. Again, a lot of people go into making these images, though, so I show you the PI, but there's whole teams of people that make this happen. So with this Hubble Ultra Deep Field 2009 with the infrared capability, we're starting to see back the reddest objects in this, right? The most distant objects we're looking back about 13.1 billion light years. Okay, so we're starting to get back only about 700 or 600, 700 million years after the Big Bang. Okay, we're really starting to get to baby galaxies, or closer to baby galaxies with this, right? Okay, I'm going to kind of go through these next ones a little bit fast, but just to show you that we've followed up with the Hubble Ultra Deep Field with additional observations in the intervening years. So I want to go back to 2009 just to point out that this observation in 2009 included all of the original observations of the Hubble Ultra Deep Field, right? And then they added the infrared observations. We don't start from scratch. We don't throw away photons. Astronomers would never throw away photons, right? We don't throw away light. So we had that original light from the 2004 Hubble Ultra Deep Field, and on top of that, right, we added the additional infrared light that we got from this survey to get the version you see here. In 2012, PI Dr. Richard Ellis and others, they took additional infrared observations of the Hubble Ultra Deep Field, added it onto this version, also in 2012, with that additional infrared light, as well as basically 10 years worth of Hubble data in the archives. Okay, so what astronomers with PI Dr. Garth Illingworth and others did was they decided, let's not just add up all the light from the Hubble Ultra Deep Field programs, but let's look in the Hubble archives, any Hubble image of that patch of sky, let's add that in. We're trying to get as many photons as we can to look deeper in the universe. And they did that, and this is what was dubbed, this is the same field of view as the Hubble Ultra Deep Field. It's the Hubble Ultra Deep Field, but it was dubbed the Extreme Deep Field, right? It's extreme. Okay, and at the time, of course, this was the deepest image of the universe. And in 2014, we get what we have now as sort of the quintessential, the best Hubble Ultra Deep Field that we have, the 2014 edition, which really added all the previous versions, but in this case, we added some ultraviolet light. So they did ultraviolet observations with Hubble. The reason why I want to do ultraviolet observations was simply because with ultraviolet, we can learn more about the star formation processes going on in these galaxies in the image. Okay, so there's added information if you add these colors. Okay, so this is what we have for the Hubble Ultra Deep Field. This is it. Now I want to say, I know I'm not giving, all the science that comes out of the deep field is due justice because I'm speeding through. I just want to say a few things before I move on about what we've learned from the deep field program, right? So again, I mentioned we've learned that galaxies in the distant universe were smaller. They grew with time. They got more massive with time. They got a bit more organized with time, right? So that's something that we've learned from the deep field program. We've also learned things like the peak star formation rate of the universe, the peak amount of the peak period of time when stars were forming at the highest rate was about 10 billion years ago, and it's been declining ever since. So we've sort of missed the party, if you will, on the peak star formation rate. Okay, so and that has a lot of repercussions about how the universe has changed and evolved since then. Okay, a big deal that come from this. So we've learned that that we have found supermassive black holes in some of these galaxies that we see about 10 to 12 billion years ago. So some of the earliest galaxies we find supermassive black holes, which tells us a great deal about how supermassive black holes have a lot to do with how galaxies themselves form and evolve with time. They're integral to the galaxy formation process. We find them early on. They're not a new phenomenon. Okay? And we've also imaged distant supernovae or exploding stars in these images, which really helped confirm that the universe is not just expanding with time, but that expansion is accelerating with time, which led the way to the Nobel Prize being awarded for dark energy. Okay? All of these things came about with the deep fields. There's just seminal amount of work that went into it. As you can see, it's about, it's about 20 years, almost 20 years worth of observations. And this final image here, I told you the original Hubble Deep Field and the original Hubble Ultra Deep Field both had about 10 or 11 days of exposure time going into it. By the time you add up all the exposure times that went into this final Hubble Ultra Deep Field, right, it's about 25 days worth, so more than double the original. Okay, all right. So I want to make the point that this has been extremely seminal in our understanding of cosmology in the universe, these deep field programs. But all the same, when you take a picture of one patch of sky, right, you still run into the question of, is that a representative sample of the universe, right? And, you could argue that maybe it is, maybe it isn't, and astronomers are arguing that, actually, as we speak. So we have really three patches of sky with these deep fields, right? We have the Hubble Deep Field North, Hubble Deep Field South, and then we have the 10 years or so of observations that went into the Hubble Ultra Deep Field, those three different patches of sky. Okay, but if we want to go and we want to sample more of the universe, we have to do something different, because we can't spend, we can't spend 10 years for each patch of sky, okay? So we have to do a different trick. We also, if we want to go deeper, we have to do a different trick, okay? So that leads us to what is now the Hubble Frontier Fields program, okay? This is what's carrying the Deep Field program along and forward. The PI here he's here at Space Telescope Science Institute, Dr. Jennifer Lotz. And this Hubble Frontier Fields program is really going to expand the Deep Field program by observing in 6 parts of the sky instead of just the original 3. Now I put them on this sort of map of the sky here. You can find your favorite constellation, but you'll notice that there are three places on the sky that you'll find the frontier fields. Okay, there's 6 places on the sky you'll find the frontier fields. I wanted to point out, if you can see it, it might be hard, but there is this sort of haze going through here. Okay, does anyone know what that might be? The Milky Way. Okay, that's the disk of our Milky Way, and you'll notice that all 6 of those positions very dutifully avoid the Milky Way. Okay, when you're trying to look into the deep universe, it really doesn't help to look along the disk of our very busy galaxy. Okay, there's gas, dust, and other things in the way. So we avoid the Milky Way. The astronomers putting this program together avoided the Milky Way, and they picked these 6 regions. But even more so to the point, if you go in and you sort of zoom in, these are digitized, ground-based digitized sky survey images, these 6 regions. What you'll notice is that there's 2 basically pointings in each region, which tells you that we're actually getting 12 new deep fields, not 6. Okay? So in each pointing, we're getting a deep field we're getting another deep field next to it. So we're really getting 12 deep fields. Okay? These squares here just show you the field of view of the 2 instruments we're using on Hubble to image each deep field. So the blue square is that advanced camera for surveys that did the original Hubble Ultra Deep Field, and that red smaller square is that infrared camera I told you about that has a slightly smaller field of view. So we're getting both cameras, so we're getting visible light and infrared data on each of those deep fields. Okay? So we're really getting 12 new deep fields with this program. And we've actually are 2/3 of the way through the program. So what I'm going to do now is I'm going to show you the 4 out of the 6 pointings or positions on the sky that we've done, okay, for the Frontier Fields program, starting with Able 2744. I kind of want you to look at these. So again, there's 2 pointings, or there's 2 images or pointings for each position on the sky, right? And I just want you to take a look at these and just tell me, right or left, which one looks like the traditional deep field, the traditional Hubble deep field, right? So there's max J0416, there's max J0717, and then max J1149. All right, which one of these looks like a traditional deep field to you? Right. The one on the right? How many people say right? How many people say left? Okay, a few people. Okay. All right. Well, it is the traditional deep field is the one on the right. That's the traditional deep field. Sometimes we call them blank fields, not because there's nothing there, but because they're in a relatively unbusy patch of sky, a relatively blank patch of sky. Okay. But what's really interesting are these images on the left. All right, which took the opposite approach. So the original Hubble Deep Field's philosophy was, let's point at a blank patch of sky and see what we see. We're using a bit of the opposite approach here on the left. We're going to say, let's look at a really busy patch of the sky. In fact, let's look at really massive galaxy clusters to see what we can learn, and I'll say why in a minute. But galaxy clusters, just so you know, are places in the universe where hundreds to thousands of galaxies are physically located nearby. Okay, so there really are clustered galaxies, right? And so the first one that was released, Able 2744, a lot of this haze and light you see are from galaxies that belong to this cluster, and of course there are galaxies in the background. Behind the cluster, there might be a few in front, but the bulk of the galaxies you see belong to that cluster. Okay. All right, so let's go back to Able 2744 galaxy cluster, and I want to point out why this is really interesting, which is if you take a careful look at it, you might notice that you're seeing the same galaxy in many places, okay? And it is the same galaxy. So for example, in this orange bubbles here, in the orange circles, that galaxy is the exact same as that galaxy, exact same as that galaxy, okay? You're seeing that galaxy in 3 places on the sky, okay? Likewise, in these green, that galaxy is the same as that galaxy, is the same as that galaxy. That's the exact same galaxy. They're not different galaxies, it's the exact same galaxy, and you're seeing it on 3 places in the sky. It's kind of crazy, right? All right, it's almost like a funhouse mirror effect, and the universe is providing this for us. Now you might say, why would we ever want to look at that for the deep fields? I mean, it's really strange. So I'll get into that. But if you actually, astronomers are poring over these data now, right? So we're getting lots of papers coming out of the frontier fields continually. And some of the papers that have come out, right, are just finding these what we call families, right? Finding these galaxies that are the same galaxy that appear multiple times in the image. All right. So why has this happened? Well, let's first do a few videos. This first one is just showing you what would happen if we were so lucky that the universe would put a gigantic lens in space for us. All right. So we have that light bulb. Let's say it's a distant galaxy. Light's leaving that distant galaxy. That lens is just lovely. It's put there. It collects that light, redirects it to our eyeball, and we would see that light, is brighter than it would be otherwise because we catch more of the light rays coming from that galaxy, right? I mean, that's really what telescopes do, right? Telescopes gather the light for us, so we can collect more light that we otherwise couldn't see with our eyeball. And the larger the glass or mirror or whatever lens you have, the more light you can collect, so you can really see the faint objects because you collect more light from them. Because otherwise that light would diverge in all directions and you would never catch it, right? Well, the universe, doesn't unfortunately put giant lenses in space for us. But there's another thing, which is called gravitational lensing, which has another way of redirecting light. Okay, this comes from Einstein's theory of general relativity, which is, we'll play this movie, which is just that if you have a massive object in space, it actually bends space-time itself, and light coming to that bent space-time has to follow the curvature of space, and it gets redirected. Much like light going through a lens gets redirected by the lens, light passing by this curved space-time gets redirected. So we'll play this video here. So you see, here's the grid of space-time. You put a star there. It really bends space-time. Here comes light, and it gets redirected and bent around space-time. And this is we've known about this, Einstein's theory of general relativity. This is why we now know we have orbits of planets around the sun that follow the curved space-time and so on. This really is gravity here, right? That's the curved space-time, and light has to follow that curvature, okay? So, naively you might think, well, we can use that to collect, to bend light just like we could a lens. So I say the mass of the star bends space-time, right? That's great, but the mass of a star bends space-time a little bit. What bends space-time more than a star? What galaxy? What bends space-time more than a galaxy? A cluster of galaxies, a lot of galaxies. A lot of mass will really bend space-time, right? And so here is another video. Here is Able 2744. I have to mention, too, Dr. Frank Summers and another person at OPO, Greg Bacon, did a lot of work putting these animations together. So thank you for that. So here's a distant galaxy behind this cluster. You can see, again, those light rays are diverging. But like that big lens in space, when it hits that galaxy cluster, that bent space-time will redirect the light. So we can actually use galaxy clusters to redirect the light so that we can see more from those distant galaxies than we could before. So sometimes we like to say, for example, that with the combination of our favorite telescope, Hubble, in combination with the universe's telescope or the universe's lens or the universe's optics, right, which is this galaxy cluster, those two in combination can allow us to see galaxies that are more distant than Hubble could see by itself, okay? Because again, it really magnifies the brightness of this galaxy. It lets us see more light from these distant galaxies. But it does, so that's the good thing, but it does produce this funhouse mirror effect, right? So this is sort of an idealized case where all these light rays come together perfectly almost at a focal point. But that's not actually what happens, right? What actually happens is these light rays are, they're diverging, and when they hit little clumps of mass in that galaxy cluster, they all take slightly different paths to get to us. And they all arrive at slightly different times, and they all appear on slightly different parts of the sky because all those light rays took weird divergent paths through that clumpy galaxy cluster. Right? It's almost like if you had glasses, but the glass maker made the glass lumpy, right? It's really not helping you. But in this case, we can actually use models to piece it together and figure out what's going on. Okay. All right. So I just wanted to do, this is a little short animation that Dr. Rachel Livermore made from University of Texas at Austin that I like to share, which is really nice. It sort of combines two iconic Hubble images. So we have M51, Whirlpool Galaxy here. And you'll also see Able 2744. Now you just do the thought experiment. What would happen if you put this galaxy behind, it's a distant galaxy. What happens if you put it behind that galaxy cluster and you just sort of move it behind the galaxy cluster? What would we see, right? And so that's what this will show you. Sort of what would we see if we put this iconic galaxy behind Able 2744? You'll see it sort of disappear, and it will show up on the left-hand side. So there it goes. It's that small. Here's Able 2744. Here is, on the left-hand side, M51. This is what happens when it passes by. All right. Play that again. This is what the universe is doing for us, right? The universe is really fun and interesting. So we'll do that one more time. So we're shrinking M51. We're putting it off to the left. And you can see at one point you're getting multiple images of that same galaxy, right? So what you see from that galaxy depends on where that galaxy is behind the cluster, because there's a whole geometry of the optics and the light paths, where that galaxy is behind the cluster and how far away it is behind the cluster. So there's the distance behind the cluster, and where along that line of sight it is will depend on what you actually see coming out the other side. Okay? Okay. All right. I just want to say you can do this sort of thing at home. Here is a actual image, Hubble image, of almost a full, what we would call a full Einstein ring, but there's a foreground galaxy here in yellow and the background galaxy in blue that's lensed around into almost a full ring. It's almost like a gravitational horseshoe. But you can sort of mimic these sort of same things if you have a wine stem at home and you have a bright light like a candle, sort of a small pinpoint of light. You can get these sort of shapes to come out. Now again, this is using glass, and gravitational lensing uses mass to warp space, so it's not the same thing creating the images you see here, but you can get sort of similar shapes that you see with this gravitational lensing. Okay, I have to mention this a little bit because this is really crucial to the program, and the Frontier Fields is really pioneering this work, which is that a lot of what we understand coming out of the Frontier Fields is coming out from not just the observations, but from the mathematical models of gravitational lensing and how this works, right? There's a lot of mathematics and physics that's going into trying to interpret what we see. And so there's a bunch of people doing modeling work. In fact, there's, I believe, 6. For the original Frontier Fields first year, there were 6 different groups around the world that typically don't necessarily work together, but for this they came together to produce models that would estimate what they would see from these clusters. Basically, these models are mathematical calculations where you calculate the mass of the cluster, and once you know the mass, you do a calculation of general relativity where you see how much warp space there is and what that would do to the light going through it. Right? And so they do these sort of models about what we might see. Here's an example of a model, and in this model, the sort of green image is the original Able 2744 Frontier Fields. The blue is a mass map, or where the mass is concentrated in the cluster, and these sort of pink, hazy, I mean, there's concrete pink lines, but there's also a haze around it. Those are places where you would find the maximum magnification for a galaxy at a very specific distance behind the cluster. And so they have to do a lot of these models, right? Because they have to do the model for, here's what it would look like if galaxies were at this distance behind the cluster. Now, what is the model if the galaxies were at this distance behind the cluster and this distance? And so there's a lot of models. And what's great about this is that science is really informing our physics-based knowledge, or I'm sorry, observations of these clusters are really informing our physics-based knowledge, but this physics-based knowledge is also informing our observations, and it's sort of it's a circular thing, right? And so what's coming out of this is, now that we have these really detailed observations of these frontier fields, which, by the way, go almost as deep as the Hubble Ultra Deep Field, the original Hubble Ultra Deep Field, however, with the gravitational lensing, we'll go even deeper, go even, as much as 10 times deeper, if you include in the lensing. So once we got these images, the modelers can then go back and take these images and refine their models. Okay, and this is really going to help us in spades once, for example, I'll talk about this, but once James Webb launches and it does similar deep field work, we'll be able to use these models because they will have been refined and so on. Okay. All right. In fact, these models were really used in 2014 to release, this was a press release in 2014, where we found a really distant galaxy in the Able 2744. What happened was astronomers were looking at this image, and they were originally looking for things that were red, okay? Because they were looking for distant galaxies, and they were looking for things that are red, because remember, things that are red may be cosmologically redshifted, they may be really distant, okay? And they found this little red thing in point A here, okay? So they found galaxy A. And they still weren't sure. This is a trick that astronomers use. It's called photometric redshift, but it's a trick that's used where they use the colors to try to estimate the distance of these galaxies, okay? But there's still, you cannot be 100% certain just with colors, because you can never know for certain, is it a red distant galaxy or is it a small, is it red because of the cosmological redshift, or is it a small nearby galaxy that's just intrinsically redder, right? You can say some percentage. I think it's 70% true that it's probably a distant galaxy, but you can never be 100% true. Well, in this case, what they did was they used the geometry of gravitational lensing and the models and so on to actually convince themselves that it is actually a distant galaxy. And what they did was they used the colors to come up with a distance where they think there's either two answers. It's either a nearby galaxy at this distance, because it's this red, or it's a distant galaxy, really distant galaxy, at this distance. They put in their model, okay, the galaxy at that distance. They basically did the light models, the light traveling through the models and so on, to say if it were behind the galaxy cluster at that really distant, position, where might we find other images of that same galaxy? And that's where they found B and C. So they didn't find B and C by looking at the image. They found B and C first by running the models to say, where would it appear in the image? Okay, if this were truly a distant galaxy. Now, if it were a nearby galaxy, it would not appear there. If it were closer, you would not see B and C. So this was a geometrically confirmed high redshift galaxy. In fact, this galaxy is we're seeing it as it looked like about 13.2 billion years ago. Okay. So we're talking about 600 million years after the Big Bang, really distant. So if say you have a family member that's 100 years old, this would be like getting a photograph of them when they were 4. Okay, it's about 4% of the present age of the universe. So we're really getting into the toddler galaxies. We're starting to look at the galaxies that may be pieced together to form current day galaxies. I wanted to show this result. I love this result. This came out earlier this year. From the MAX J1149 galaxy cluster. This is an example of a lensed supernova. Okay? First time it's ever been observed. These 4 objects here are an exploding star called a supernova that we're seeing 4 times. Okay? Now, this was actually predicted that we should be able to observe such a thing, but until this year it was never observed. Okay? And what's really cool about it is that the astronomers looking at this. So you see, this is what we would almost call like an Einstein cross. Everything's named after Einstein. It's general relativity, after all, right? So this would be almost like an Einstein cross. You see the 4 points here. What's really doing so there's the foreground cluster. That orange blob here is a galaxy in the foreground cluster that's doing the lensing. And you see that there's a spiral galaxy, and there's a spiral arm that falls behind it that's being lensed. Okay? And you're seeing that supernova that's going off in that spiral arm in 4 positions. Okay, it's really amazing. And in fact, they did the modeling, and if I get this wrong, someone will correct me, I'm sure. Someone watching YouTube is probably like that. But they were actually able to time, these appeared at different times, okay? So the lights took slightly different paths, and these supernova, I believe, were maybe days apart in appearance, I believe, something like that. It wasn't a long time, but they did appear at different times, and I believe it was maybe this one, then this one, this one, this one, or it was some combination, but they actually could do the models and figure out that they had different light travel times. What's also cool is that this is lensed by that one particular galaxy, but this whole spiral galaxy is actually lensed by the cluster in 3 different positions. This is the same galaxy. That's the same galaxy. Okay? All right? And they actually found out that, I can't remember now, but in one of these, the supernova, we should have observed it about 20 years ago if we were looking. I believe it was about 20 years ago. And I believe within the next 5 years, we should see it in the other one. So they have actually now a prediction based off of our models of when we should see, basically, it's like a TV show rerun, right? We're watching Seinfeld again. But we should be able to see when that supernova goes off again because we have the models that tell us that that supernova is taking slightly longer light travel time to get to us from one of these others. I can't remember if it's that one or that one, but incidentally, I'll give you a resource where you can find all this information at the end if you want to learn more. The people in the Office of Public Outreach here created some wonderful videos too to showcase this, and I can show you where you can find those. Okay. So I just want to get back to this sort of picture, right? With Hubble and with the frontier fields, we're really getting back into what we would call toddler galaxies, okay? We're getting back into the earliest galaxies, some of the earliest galaxies in the universe, right? And that really is, because we're using the gravitational lensing. Also, we have, the capability of looking in the near infrared for the really high cosmologically redshifted galaxies. So we're really getting back further in the universe than we've ever done before, which is great. But we're reaching sort of Hubble's capabilities, if you will, of looking in the distant universe. We might need something else if we want to look back even further, right? So the James Webb Space Telescope is going to launch in a few years, and this is a mostly infrared, really sensitive telescope, right? And one of its science goals, science themes, is called first light, which is to see the first light from galaxies and stars to form after the Big Bang. That's one of its goals, its stated goals, okay? It's really going to try to find those really baby pictures, right? Now, if you were taking a picture of a baby on Earth, right, you might have to go to a nursery or something like that, right? You'd have to go to a special thing. We need special tools to see these baby pictures. We need James Webb, right, to see these baby pictures, all right? And so that's James Webb is really going to help push the field, the sort of deep field science forward. And again, really benefit from the frontier fields and the modeling that's going on to the lensing and so on. Okay, these are, you don't have to read this. But, for those on YouTube, you can pause it and really mull over image credits. I wanted to leave you with additional resources. So you can find out more information. We have our hubble25th.org website. You can find out a lot of, we have science stories and images, and you can find out about the deep fields. In fact, it's impossible to talk about the deep field science without leaving a lot out, and I left a lot out. So I left entire programs out. You can go online and you can find out about the Candles program, the Goods program. There is even a program called CLASH. These are all acronyms, by the way. You can find out what they mean online, but CLASH really helped tell us that we can do this sort of gravitational lensing science in the deep fields and so on. So there's a lot of deep field science that I left out of this story that you can find online. Also, we have a general public purpose blog called frontierfields.org. Both Frank and myself write on this blog. We post videos. A lot of the videos that I didn't have time to show you today will be there. And again, this is just for general audiences, and you can take a look and see what we have there. And I believe that's it.
All right.
Thank you.
All right, thank you, Brandon. That was wonderful. And if you are anything like the YouTube chat folks, you have way more questions than we can possibly answer tonight, because I was typing out answers on YouTube the whole time you were talking there. All right, so down front, what do we got?
Will Hubble and Webb overlap in producing?
So the question is, will Hubble and Webb overlap? And the answer is yes, absolutely. There is a current initiative right now called Hubble 2020, which is mapping out the science goals of Hubble over the next 5 or so years. And part of that is at least a year overlap, science overlap with James Webb Space Telescope. Yeah. So part of the mapping out of the science goals is what are the things that we really think we can do well when we have both those observatories working together? It's a good question.
Okay, over here.
We have these wonderful names for stars and for galaxies that none of us can remember. Is there a catalog that has beside that name, how far away is it?
Yes. So what I showed you for the frontier fields, for example, are catalog names Max, J, whatever, Able 2744. Some of them actually do have sort of more colloquial names, like Able 2744 is also called Pandora's cluster. But we do, if you go on Frontier, so all those catalogs do have basically, and you can go online to find distances to the clusters. Now, of course, when you're looking at these sort of, core samples through the universe, you're really sampling things at a lot of different distances, right? So we do have distances to the clusters, and you can find that on frontierfields.org right here. We have all those numbers, so you can learn about each cluster, and it'll tell you what those are. But some of the most, in my opinion, interesting science is coming about learning about the distances to the things behind the clusters, the really distant things. And those, again, are taking a lot of work to understand, and which is what I talked about here. But once we start finding those distant things, we really like to put those numbers up. But yeah.
And let me just add to that if you want a general purpose catalog if you want to look up something and get a decent estimate, the NASA Extragalactic Database, NED, that's a really good, just a catch-all type thing. It may not have the absolute perfect information, but it'll have a generally good enough to start with. Okay, in the back in the bright color.
Yeah. In this morning's Sun, there was a story about the telescope that's here at Hopkins being disassembled for transport down to Chile. And what's the relationship of that telescope to what we've been seeing here? Or maybe another way I'm looking at it is, what is that telescope going to be able to do that Hubble hasn't done or can't do, perhaps?
I honestly am gonna. I honestly don't know. I don't know which telescope is being moved from Hopkins to Chile. I haven't heard that story.
Do you have a name for that telescope? Did they give you an acronym?
CLASS, I think. CLASS.
It's the 104.
Okay. Neither Brandon or I saw that article. And,
yeah, sorry.
he has to come back. Who knows?
Hi everyone, my name is Duncan. I'm going to be doing the observing afterwards, but I also work on the CLASS telescope, and that's going to be measuring cosmic microwave background polarization radiation. So that's, I'll defer to the person with the microphone maybe to explain that a little bit.
Okay, well thank you. So for people online that didn't hear, he said CLASS telescope is looking at the cosmic microwave background and polarization of the cosmic microwave background. So I said, looking at the deep fields in the deep universe, I mean, if we want to be technically correct, it's sort of the earliest images we have of the universe are the cosmic microwave background, right? This is a time, 300,000 or so years after the Big Bang, before galaxies. And, this was the sort of remnant glow of the Big Bang, if you will, that has cooled in the intervening 13.8 billion years, and now basically emits in microwave light. And there's a whole big, realm of study in cosmology about studying the cosmic microwave background, its polarization, sort of telling us the earliest structures of our universe and how that can tell us about how structures formed in the early universe that did produce galaxies we see today, and superstructures of galaxy clusters and things like that. I don't know if you wanted to add anything to that, but.
No, that's, cosmic microwave background observations are definitely a different realm. But I got to add to it from online. It says, how will the WFIRST telescope deal with some of this stuff?
That's a great question.
So first explain what WFIRST is so that the audience here.
I'm going to mess up the acronym probably, but WFIRST is a
Wide Field Infrared Space Telescope.
Right.
That much I know.
Right. So it's wide field. So it's basically it's a gift to NASA is what WFIRST is. So it's a leftover spy satellite that they had, that the National Security, NSA I believe, had that national. Oh, okay. So some government agency has Hubble quality spy satellites sitting around in storage, 2 of them, and they gave one to NASA, and so it's great. I should say that it's not totally free, right? Because it basically was, the telescope was basically the mirror and the structure of the telescope, but we still have to produce all the instruments and things that we want to put on the telescope. So it's not totally free. We have to launch it. But it's a great start. And what they're going to do is we're going to use that for basically Hubble quality data, if you will, but wide field. So we can do these sorts of deep fields, but we can do them in a much broader field of view. We can cover much more of the sky than we could with Hubble. Okay, I don't know if you have the...
The Hubble images are 16 megapixels. Every image from WFIRST, I believe, is like 230 megapixels. So it will cover a much larger field of view at similar resolution to Hubble and enable us to do this kind of study in spades.
Yep.
The actual problem with things like that and like the dark energy camera and other things is that we're almost going to get too much data. We've got a project for next decade that's going to produce over 2 billion pixels per image. So we're getting going to get a lot of data in astronomy, and that's actually one of the a difficulty, but a difficulty we'll be happy to try and solve.
Sure, job security, right? Right, and just to give you some numbers, WFIRST is scheduled to launch in the sort of 2020s time frame. I believe early 2020s is the sort of time frame they're looking for WFIRST.
Okay, right here.
Can you comment on how the astronomers know that the different images are identical from the lens?
Right. So a lot of that has to do, again, with the models. Okay, so when they have the models of the basically light path, they can do estimates of their distances, and they can run the models, and they can sort of tell this one if this one belongs with this one. There's also one nice thing about the gravitational lensing is that it doesn't change sort of the intrinsic colors of the galaxy as it goes through the lensing. So the colors stay the same as if they weren't lensed, and that sort of helps you piece together things and match galaxies that were basically similar colors and similar traits. The sort of be-all, end-all, if you wanted to if you don't, if you don't have necessarily the models working perfectly or whatever, sort of classically what you would do is you would take a spectrograph of the galaxies. And if the spectra mirrors out, if the spectra looks basically identical or relatively identical, then you can basically say, yes, so those are the same galaxies. And that's traditionally what they've done. But with this new method we're pioneering with the sort of geometry, with the models of gravitational lensing, it's helping pinpoint another way of finding what we call these families. So I would say the models are sort of the new way that people are pioneering, yeah.
Just a quick one.
Yeah.
Sorry, Frank. What's the magnitude of these lenses?
So the magnitude is, so the sort of the magnitudes of the Hubble Ultra Deep Field get down to about 30th magnitude.
30th?
Okay? 30th for the Hubble Ultra Deep Field. The frontier fields get down to close to that, 28 point something. But if you add in the lensing, you can get in actually 10 times deeper than you could, I believe, with the Hubble Ultra Deep Field. So you go back, you go even further. You go, I don't know what the magnitude is when you include lensing, but if you include lensing, you go beyond 30th magnitude. So, yeah.
Do you see any evidence of lensing in the very early material that you're looking at?
That's a good question. Do you see evidence of lensing in the original Hubble Deep Fields? Yeah. Now, I mean, technically, there's always going to be lensing everywhere because everything bends space, and but is it enough to notice it? We picked the Hubble Ultra Deep Fields are not in places with a lot of gravitational lensing because there's astronomers sort of divide it out into what we call major lensing and minor lensing. Okay, major lensing is sort of what you see with these frontier fields where you see multiples of the same galaxy, and you really need a really massive galaxy cluster to produce that. Now, minor lensing effects you can get from individual galaxies lensing background things. And I don't know if we've actually detected that in the original Hubble Deep Fields. We may have, but it's a much harder effect to detect because it's not as noticeable. The lensing isn't as great. But it is one thing that we're pushing on. I mean, this isn't the Hubble Deep Field, but I can tell you that within our own galaxy, there's a whole other use of gravitational lensing, which is the search for exoplanets with gravitational lensing. So within our own galaxies, if you mirror enough stars and you notice that they basically brighten with time, right? There might be a lensing effect there. There might be a little planet that lensed it or something. So yeah.
The perspective is that what you're looking at, even in the early deep field, is something that's three-dimensional. All these galaxies are not in the same plane. So that, in theory, the lensing and its effects should be perceptible.
I don't know if they're perceptible. They're certainly there. I mean, they're certainly lensing. I mean, anytime you have curved space-time, there's certainly lensing. But again, it's my guess is that it's probably minor lensing that's probably very, very hard to notice in the original deep fields.
And really, to get the kind of lensing that he's shown you here tonight, we're talking about some of the most massive clusters in the universe, okay? Yeah. We're talking 10 to the 15th solar mass clusters. A 10 to the 12th solar mass galaxy will provide some lensing, but the effects are not going to be the strong lensing that he's shown you here tonight. There is, in order to measure what we call weak lensing, actually W-first would be good for weak lensing, because you need a wider field in order to measure the statistical properties of a large collection of galaxies in order to measure the very subtle effects of what we call weak lensing.
Right. I should say that's right. That's what we call it. We call it strong lensing and weak lensing. So, and what I showed you with the frontier fields is mostly strong lensing. That's right.
Okay. Anybody in the back? Because I always pay attention down front. I want to make sure I get the people in the back. All right. Down here.
When you see three images of the same galaxy, is there a loss of brightness? Does the brightness get scattered between the three images? Did you actually lose 3 times the brightness, maybe, some way?
Certainly you will. It's not as bright as if the universe had concocted such a way where it was what we maybe call in focus, where it was all in one spot. Certainly it's not going to be as bright as if we had that. That's certainly true. But you know, astronomers are very clever at finding ways to combine photons and make things, get as many photons out as you can. So you can find ways to try to use the knowledge of the 3 individuals to get some information about the galaxy.
Yeah, but also recognize that if you've got light from this object and it's going this side of the cluster and light going over that side of the cluster, if there was no cluster there, you'd only get the light that's headed straight towards you. So you're actually taking different light beams coming from the same source, so there's no reason why this source should be any different from that source if they're covering the same area. And as you change the area that you see it through, that's what will change the light. But recognize that the light is coming off in a sphere from it, that you're taking different pieces of that and redirecting it towards what you're seeing, right? So, okay.
You have to worry about the geometry because it's going to appear, disappear.
That's the amazing work that he was talking about in the modeling, okay? The fact that he got 6, he actually lied a little bit. He said 6 people that don't usually work together. No. These are 6 teams that absolutely compete against one another and are the fiercest rivals. The fact that they worked together on this project was really quite amazing, okay? Right. Astronomers left their egos at the door and they worked together to solve these really, really difficult problems.
Last one.
Okay?
You got a photon. It's been traveling for 13 billion years. It's been corrected. Does it lose any energy at all while being lensed? It does. What happens?
This is a tough question. We've gotten this one before.
The cosmological redshift, which changes its wavelength, right?
Right.
Okay.
That's the only way it changes. It changes the wavelength.
Yeah, I mean, again, I think one thing to remember too is that, also it's a relativistic event, and what you observe and what we observe really depends on space and time and where you are in the universe. And so, that photon looks to us to be redshifted, but it would appear to be very different if you were in a different location in space and time. So, a lot of it depends on the fact that we are where we are is how much it looks redshifted. If we were somewhere else, it wouldn't. It's the same photon, but it wouldn't look as redshifted.
All right, any final questions? All right, one more over there. Last question.
How do we know in what direction to even look for the Big Bang? If we're looking back that way, of all the directions we can look, how do we begin to even know which direction to look down that cone that you grab?
It's a great question. So the question again was, in what direction do you look for the Big Bang, basically, was your question. You have to be pointing in the right direction, right? This is actually a misconception, though, that that you can get from that illustration that I showed earlier, where it showed the sort of core sample and looking back, right? In reality, every place is the Big Bang, right? In reality, we all came from the Big Bang. There is no center to the universe, right? So the Big Bang was everything, and at time, everything sort of expanded with time, and that's why no matter where you look, you find this cosmic microwave background, you find this remnant glow, it's everywhere, right? Because everything was part of that Big Bang. So it is a misconception to think that there's a center of the universe or a place you could look at to find the Big Bang. Basically, no matter what direction you choose, if you look back far enough, you'll get, you can get back close to the Big Bang, right? Now, it turns out there's a limit. You can't get actually to the Big Bang. The limit really is the cosmic microwave background. For physics reasons, we can't see. The universe is opaque. It's not see-through at that point. So we can get back to the cosmic microwave background in any direction we look.
Okay, so we have observing at the Maryland Space Grant Observatory across the street. Maybe you'll see aurora. Maybe you'll see, I know that there are planets up in the morning sky, so I don't know what's up in the evening sky. Next month, December, Lucy McFadden talking about the Dawn mission. Let's give Brandon one more big hand. Upstairs?
Well, it'll open for you on the way out. Oh, really?
Okay, yeah. The downstairs parking garage is always open. That's the only one that they open for the public lecture series.